Math 1314, Tyler Junior College, Section 3.5, Rational Functions, Identifying Vertical Asymptotes. In the previous video, we discussed arrow notation, saying that as x approaches a value, then y approaches a value, sometimes specifying x approaching a value from the left or x approaching a value from the right. And we had that discussion based on this graph. Recall that the function we were looking at was f of x equals x squared plus 3x plus 2 over 2x squared minus 8, and the domain was all real numbers except positive and negative 2, because those values made the denominator equal to 0. In our discussion of the graph, and prior to that, the discussion of the tables of values, we had noticed that there was a vertical asymptote at x equals 2, which was one of the numbers excluded in the domain. But at the other number, x equals negative 2, there was actually a hole in the graph. Specifically, there was a hole at negative 2, comma 1/8. Both negative 2 and 2 were the values excluded from the domain, so that suggests that excluded values are places to look for vertical asymptotes and for holes. But why is one of them a vertical asymptote and the other one not? The reason's a little stealthy, but pretty easy to explain. In order to explain why x equals 2 was a vertical asymptote, but x equals negative 2 was a hole, let's take a look at the reduced version of this function. Now, what do I mean by reduced? Well, in a fraction, reduced means no common factors between the numerator and the denominator. In order to see the reduced version of this function, we need to first factor it. The numerator, just being a trinomial, is pretty easy to unfoil. It unfoils or factors into x plus 1 times x minus 2. Excuse me, x plus 1 times x plus 2. The denominator has a greatest common factor of 2, but before I take it out and say, look, it leaves x squared minus 4, x squared minus 4 is a difference of squares, so it factors into x minus 2 and x plus 2. Do you see the common factor? The common factor of x plus 2 can cancel. And so the reduced version of this function is x plus 1 over 2 times x minus 2. Let's call this FR for the reduced version of f. This is not standard notation. I literally just made it up. So how can that help us identify vertical asymptotes versus holes in the graph? Well, look at the reduced version of the function. There's only one number I can put in this that would cause the denominator to be 0, and that's x equals 2. That's where the vertical asymptote is. Well, what happened to the other factor? And what about this hole? Well, look at the factor that was canceled. Now look at it before it was canceled. Well, it's not over there. Pretend it's not canceled yet. What value of x would make this canceled factor equal 0? Answer, x equals negative 2. So we're starting to see something that might suggest you're a vertical asymptote, but you're a hole in the graph. And it has to do with the original function versus the reduced version of it. If a value of x makes the denominator of both the original function and the reduced function equal to 0, then that value of x represents a vertical asymptote. But notice that although negative 2 makes the original denominator equal to 0, it doesn't make the reduced denominator equal to 0. A value that makes the original denominator 0 but not the reduced denominator represents a hole in the graph. So to summarize, x equals 2 is a vertical asymptote, which I'm going to abbreviate VA, because now we can say that it makes the denominator equal to 0, but that's equivalent to saying that it makes the function undefined. Because f of 2 is undefined, meaning it gives a 0 in the denominator, and the reduced f of 2 is also undefined. So if you make the denominator 0, but then I reduce you and you still make the denominator 0, you are a vertical asymptote. But x equals negative 2 is a hole in the graph because f of negative 2 is undefined. I can't put negative 2 into the original function, but the reduced f of negative 2 is not undefined. So if you make the original denominator 0, but not the reduced denominator, you're a hole in the graph. But if you make both the original and the reduced denominator equal to 0, you are a vertical asymptote. And one more thing about the reduced function, this one over here. If you were wondering where this 1/8 came from, it's the value of the reduced function at negative 2. The whole is at the reduced function evaluated at negative 2 gives us negative 2 plus 1 on top, and in the denominator, 2 times negative 2 minus 2. The numerator is negative 1. The denominator is 2 times negative 4, which is negative 8, and that's the y-coordinate of the whole. So to summarize, to find a vertical asymptote, actually I should not just summarize, I should write this on the board, because all I've done so far is explain relative to this specific example. What we need is a technique for finding vertical asymptotes and holes for a general function. So, here is how to find vertical asymptotes and holes. How to find VAs and holes of f of x. Number 1, solve denominator equals 0 for f of x for the original function. Number 2, if possible, because it's not always possible, factor and cancel to reduce f of x to f r of x, so the reduced version of the function. Any solution to 1 that makes f r of x undefined. Let me pause for a second and remind you what I'm saying here. If we solve this equal to 0, we get 2 and negative 2. So 2 makes this undefined, but it also makes this undefined. Any solution to this step that makes the reduce function undefined is a vertical asymptote. Otherwise, comma, x, comma, fr of x is a hole. In other words, if a solution, and you know what, I should probably give this solution a name instead of just using x being a generic input. So let's say any solution, we'll call it C, but I'm going to write it in red so it stands out a little bit. Any solution C to the first step that makes fr of C undefined is a vertical asymptote. Otherwise, C, comma, fr of C is a hole. Let's take a look at a specific example that we don't already know the answers to. Let's say f of x equals, we'll keep it kind of simple, x squared minus 9 over x minus 3. F of x equals x squared minus 9 over x minus 3. And the question is, what are the vertical asymptotes and what are the holes? And by the way, there's no guarantee you'll have either. If your denominator has no real zeros, then there are no vertical asymptotes or holes. But you can have one but not the other. You can have a vertical asymptote but not a hole, or vice versa. So let's take a look at this one. In order to locate both of these, you start by solving the denominator equal to 0. Okay? And that gives us, now be careful, this is the double arrow, which is the symbol for the word implies. That implies that x is equal to 3. This number is not in the domain. It makes the denominator 0. Step 1. Step 2, we need to reduce. F of x equals. The denominator won't factor, but the numerator will. The numerator will factor into x minus 3 and x plus 3. That gives us a matching factor. And now the denominator is just 1, so my reduced function is just x plus 3. It's important to point out, kind of important to point out, that these two functions are not actually equal. The equal technically falls apart here, although I'm not going to question it. The reason the equal falls apart here is prior to canceling, I can't put 3 here, but after canceling, I can. So they're technically not equal. They're equal for all values of x except -3, because -3 makes this undefined. All right, so we reduce the function to its reduced form, so in this case it's just x plus 3, and then we check to see what happens when we put the 3 into the reduced function. When we put the 3 into the reduced function, it just says x plus 3. So what does this mean? Well, if the solutions up here make this undefined, it's a vertical asymptote. This is not undefined. And what that implies is that x equals 3 is not a vertical asymptote. So, that means this ordered pair is a hole in the graph. So, 3, 6, the number that was not in the domain and the output from the reduced function, is a hole in the graph. Had this fraction been reciprocated, x squared minus 9 on the top, x minus 3 on the bottom. That's how it looks right now. Had it been reciprocated, x squared minus 9 on the bottom, x minus 3 on the top, then we would have solved this to get 3 and -3. When we flip this, we would have had 1 over x plus 3. In fact, I think this is worth writing. It's pretty easy to explain. In fact, this is easy to do. It's just tricky to put into all the words. If we had g of x equals x minus 3 over x squared minus 9, then if we solve the denominator equal to 0, we would get plus or minus 3. The reduced version, without going through all the details, would be 1 over x plus 3. Think about it. Putting in -3 is still undefined, but putting in +3 would give us 1/6. So that would tell us that if it were this, then -3 would be a vertical asymptote because it's still undefined, but at 3, 1/6, we would have a hole in the graph. If you're wondering what would this graph look like, this one, it's actually pretty easy to draw. All you have to do is draw the reduced functions graph with the correct asymptotes and or holes. I know what this graph is. This is in slope-intercept form. Slope of 1, y-intercept of 3. So this would be a real easy graph to draw. Y-intercept is 3. Slope is 1, which means a perfect diagonal line, except over here at 3, 6, I would have to take out a hole. So So that's how you make holes in graphs. Holes in graphs occur when you have canceling factors that totally wipe each other out like these two did. Don't worry, we're going to do more graphing as the main point of a video. I just wanted to follow up on that one. Ooh, long video.